Greetings. So we have here the first day of derivatives, and this is going to be the derivative by definition. So one of the main problems in calculus is used to find the rate of change or slope. So just kind of recall what you know about rate of change or slope from Algebra 1. So we know that the rate of change formula from Algebra 1 was the slope, m, is y2 minus y1 over x2 minus x1. And to use this formula, you needed 2 points, okay? You needed an x1, y1, and then an x2, y2. And we realized that that wasn't very useful if you had to, say, find the slope of a parabola or something that was not growing constantly or shrinking constantly at a constant rate. So in pre-calculus, you talked about the average rate of change formula, and we said that the average rate of change, okay, average rate of change from pre-cal was f, we said f of b minus f of a all over b minus a, but really that's the same thing as f of x2 minus f of x1 all over x2 minus x1. So it's basically the same formula, but now we're kind of taking an average. So for example, if you were kind of working with a parabola, you would take 2 points on that parabola and find the slope that connected those 2 points, and we'd say that's the average rate of change over that x interval. So that was kind of, how we solved this problem last year, but now calculus lets us find the average rate of change in a different way. And when we did that in pre-cal, really what was happening, I can sketch it out here. So you have, some sort of curve. We'll just do something like this, okay? And if we have a secant line that kind of connects those 2 points, right? So let me switch colors. We'll say that there's a secant line that maybe goes through that curve, okay? And I'll call that the secant line, okay? And what it did is it used those 2 points, okay? And then it used the corresponding x and y values. So if you drop this down, we might call that a. Drop this down, we'll call that a plus h, right? So this distance here would be h. And then the 2 different outputs, right? So here, this y output would be f of a plus h. And this y output here would just be f of a. Okay, so again though, it relies on having those 2 points in order to calculate it. Okay? Now, when we take a look at this, our goal in calculus is to be able to find the instantaneous rate of change. So we want to be able to find the instantaneous rate of change basically by moving these 2 points closer together. You could almost think of this axis almost like as time or something like that. But I want to know if we're taking that distance, that h distance, and we move it closer and closer and closer together, what's going on at just an instant? In other words, what's happening? How would I find the instantaneous rate of change or the slope given just 1 point? And that is kind of the crux of calculus. Like why, how do we do that, and what can we do? Okay? So how do we do that? If we only had 1 point, an instantaneous rate of change, you only have one point, how would you find the slope? And the answer to that is really by taking that h distance and moving them closer and closer and closer together. Okay, this is a key part, so I'm going to kind of mark that down here. So key concept in calculus. Okay? Okay? Calculus helps us, okay? Helps us find the instantaneous rate. It helps us find the instantaneous rate of change using 1 point. Okay, notice that before we had to use 2 points, but now we are going to be able to find the instantaneous rate of change using 1 point. So let's just talk about some notation, okay? So in calculus, closer and closer translates to a limit, and we've already spent, a few weeks there talking about limits, and the slope of the tangent line has a special name called the derivative. Guys, definitely need to know that. The slope of the tangent line. When you see those words, you should be thinking derivative, okay? So there's a couple different ways that they might ask you about a derivative. So they might ask you for a derivative at a particular x value. Like they might say, what's the instantaneous rate of change at, x equals 3 or something. So if they want that, the notation here, this f prime at a, so this means the derivative at a, that little tick mark there, you read that as prime, f prime, or you could just read it as the derivative at a. And what it's going to be is, it's, no surprise, the limit as h goes to 0. And again, going back to this picture, if you have this distance here as your h, okay, and we're squeezing it back and back and back so that the distance between the 2 points goes to 0, that's really finding the slope at an instant. And we're going to it's going to look like a slope formula. Well, it was f of a plus h minus f of a, right? These are both y values, so it's y2 minus y1 all over. And then when you think about the x values, well, if you're saying a plus h minus a, well, that's where that h comes from, right? A plus h minus a, well, that just gives you h. So it still is that traditional slope formula, it just looks a little different when we simplify it. If you are asked to find the derivative at a particular x value, again, like x equals 3, you will get a numeric answer, like, 7, 1/3, -2, okay? Sometimes they'll ask us to find the derivative as a function, meaning given an equation of a line, what is the slope at any x value? So if your answer is numeric, here, if they ask you to write the derivative as a function, you might still have an x value in your answer. And they would just write that as f prime of x, or the derivative at x, and that's going to be the limit as h goes to 0. Again, that distance between the 2 points goes to 0, of f of x plus h minus f of x all over h, okay? And then the alternate definition of the derivative, sometimes you'll see this written out, so it's the derivative. Sometimes they'll use a c, okay? And it's going to be the limit as x goes to c of f of x minus f of c all over x minus c. Okay, so sometimes you'll see that one. That one's not quite as common. Again, this first one, your answer is going to be a numeric output. The second one, your answer is going to have an x in it, okay? Because then you'd be able to plug in at any given x value to find the instantaneous rate of change at any point on that equation or that function. And then this alternate definition shows up sometimes in like the multiple choice of the AP exam. So we'll just have that to be familiar. Okay, so moving right along, we're going to have the steps for finding the derivative. So this is the long way, and I know some of you in physics have probably already kind of learned a couple shortcuts, and we're going to, spend some time learning all of the different ones. But it's really important that you know where this comes from, because of the way that they ask questions sometimes on the AP exam kind of requires you to realize this definition using the limit definition, okay? And you'll hear me say that sometimes. I'll say, use your limit definition of the derivative, okay? So your steps for finding the derivative kind of the long way. So you're going to find f of x plus h, if you're finding the derivative in general, or find f of a plus h if you're finding the derivative at a particular x value. And then plug in what you got here into that big old formula, and then compute it. So that might require some extra steps. Okay, we'll start with a simple polynomial here. We just got a little trinomial there. And I kind of like to kind of break it up. So first I find f of x plus h. So from pre-calculus, or your composition of functions there, I know you did that in Algebra 2, whenever you see f of something in parentheses, that means that's the x value. So wherever I see x, I'm going to replace it with x plus h. So it's going to be 3, and then x plus h squared, because there's a x squared, and then plus 5, and then instead of an x, I'm going to replace it with x plus h minus 3. Okay? So now just do a little algebra and kind of FOIL that out. So you've got 3, and then turn this into a FOIL problem would result in x squared plus, so you'd have an xh and another xh, so 2 xh's plus h squared, and if that's confusing, go ahead and write that out in a separate step, plus 5x plus h, oh, I should have distributed that, minus 3, I'll do it in the next line. So in the next line, I'm just going to go ahead and distribute, and then combine like. So we can go ahead and distribute, so we get 3x squared plus 6xh's plus 3h squared plus 5x plus 5h minus 3. And unfortunately, when you're kind of looking at that, you're hoping that something's combined, but they don't. So that's kind of why I do this kind of in its own separate step. And now I'm going to go ahead and plug in to the formula. So remember that proper derivative formula here, remember it says that the derivative is going to be the limit, and I'm just copying this from the previous page, but I like to have it here so that I have something to reference. So this is our limit definition of the derivative. Okay? So now this is this huge thing here, and then it's just minus the original. Make sure when you're doing this minus the original, basically you have to put this trinomial here in parentheses, otherwise you're gonna miss your negatives there. So I'm gonna write it as the derivative of x equals. I'm gonna recopy this. Okay, so it's just recopying that, and then I'm going to put the other part in parentheses. So plus 5 minus 3, parentheses, minus, and then parentheses 3x squared plus 5x minus 3. Okay. And some of you will go ahead and distribute that all in one step. That's fine. So there's this, there's that, and then it's all of this divided by h. Right? Oh, I forgot my limit. So the limit as h goes to 0. I can fit it in there. Okay. So we've got the limit as h goes to 0. Now, obviously, you can see when I go to take my limit here as h goes to 0, that's going to give me some really big problems. Okay? I'm going to kind of end up with that 0 over 0 deal. So my suggestion here would be to distribute this negative and then see if anything kind of cancels out, okay? So we've got the limit as h goes to 0, and we'll do 3x squared plus 6xh plus 3h squared, 5x plus 5h minus 3, and then it'll be minus 3x squared minus 5x plus 3 all over h. Okay? So once you get to there, you can hopefully see that this takes out that, and I've got a plus 5x and a minus 5x. I got a minus 3 and a plus 3. So you can kind of start to kill stuff off. And again, when you plug in h equals 0, you're like 0 over 0. That's an issue. But if you notice that the terms that are left, they all have a GCF of h. So I'm going to go ahead and pull out that GCF of h, and I get 6x plus 3h, there's still an h there, plus 5 all over h. Now something good is about to happen, because now finally these h's will cancel. And so now I'm left with the limit as h goes to 0 of 6x plus 3h plus 5. Well, now you actually evaluate the limit. As h goes to 0, this piece goes to 0, and I'm left with 6x plus 5. Okay? So there's the final answer here. Notice that since it said find the derivative of the function, that my answer still had a variable in it. I was not left with a numeric answer. Okay? So go ahead and do this. You try it. Okay? Again, first try to find f of x plus h, and then plug that in to the derivative formula by definition of the limit. and reduce it out and see what you get. So I encourage you to pause the video. Okay, so here, once you plugged in an x plus h wherever you saw an x, you can kind of simplify and reduce that. Watch your negative there because you're distributing that -4. And then you go ahead and you take this whole expression and you plug it in minus the original. So when you subtract the original, this turns to a positive 4x squared, a negative x, and a plus 1. I kind of did that all in one step. The idea there is that a bunch of stuff is going to cancel, and then it's going to leave you with a GCF of h in that numerator. So I pulled out that GCF of h. Then you can cancel those h's, so you're left with the limit as h approaches 0 of just this negative 8x minus 4h plus 1. Again, pay attention to your limit on what is approaching 0. It's not the x, it's the h. So if you plug in a 0 for the h, right, you're going to be left with negative 8x plus 1. Okay? So those are both two examples of you having an x in your answer. Okay, let's move on to the next page here. When you're going to be asked about an example at a particular x value. So these examples are going to be really special. Your calculator cannot help you with those first two. Your calculator is able to do this, and I'll kind of go through how to do it on your calculator. But if you're ever asked to evaluate a derivative at an x value, please, please, please make a note that that is way simpler to do on your calculator. But I'm kind of wanting to go through the process, so we'll go ahead and go through this process of finding it this way. Okay, so this time we are going to, instead of finding f of x plus h, we're going to find f of 3 plus h, because that was the a value, right? A plus h, here the a value is 3, so we just plug that in. So what does that mean? It means wherever you see an x, you go ahead and use this. And by the way, for those of you that are in physics and maybe kind of, on those first couple examples, you were like, well, I know a shorter way to do it. Well, yeah, that's fine. Your way isn't going to work on something like this, though, so here you go. All right, so we're going to, wherever we see an x, we're going to plug in a 3 plus h there, okay? And I'm going to go ahead and clean that up in this step. It'll just kind of save me some cleaning up to do. So what is that going to be? That'll be a 6 plus 2h, but then I still have this plus 3, so I can actually reduce that a little bit more, and I'm going to say 2h plus 9, okay? And now when we find the derivative, okay, so to find the derivative at 3, that's how you would read that, find the derivative at x equals 3, okay, is going to equal, let me not forget the limit this time, it's the limit as h approaches 0 of, if you needed to reference what it was, so this is what we're doing, we're taking what we just found minus the original all over h. So we're just plugging into that formula from the first page there. So when I go to plug in, it's going to be the square root of this thing that I just found, so that's 2h plus 9 minus the original, so minus the original all over h. Okay, so we've got that. And so this obviously doesn't look beautiful, but we can probably make it work here because we didn't plug in a 3 here yet. We know that this x is going to be a 3. So when we do this at 3, this is going to be a 3, okay? And we can kind of clean it up a little bit more. So I'm going to go over here and say that's equivalent to the limit as h approaches 0. It'll be still the square root of 2h plus 9. But now it's going to be minus the square root. Well, that's going to be 6 plus 3, right? So that's the square root of 9, or you can write 6 plus 3 there, all over h. And so that's just going to give me a minus 3 there. So at first glance, you're like, oh, this is getting easier. But in reality, it really doesn't help us with cleaning it up at all, because now you're left with this. And of course, when I go to plug in h equals 0, I get 3 minus 3, which is 0, over 0. So I end up with that indeterminate form of 0 over 0. So that kind of tells me, oh no, I need to do something. Well, I see a square root. So normally when I need to do something like that, I factor, or I multiply by the conjugate, something like that. since I see a radical, the conjugate seems to be a good choice. So what I would do here is I would multiply by the conjugate. So that's going to be 2h plus 9 and then plus 3 over that radical 2h plus 9 plus 3. Again, it's that undercover 1, so I am allowed to multiply by it. Okay, and the reason I did that is because when I took this limit, I got 0 over 0, that indeterminate form. So I'm saying that that's mathematically equivalent to the limit as h approaches 0. And then when I FOIL this out, this times this, well, that is just that thing squared, or squares and square roots. You could say kind of kill each other off, so I end up with this. And then I end up with a positive 3 radical junk, and then minus 3 radical junk, so those cancel. And negative 3 times positive 3 gives me a negative 9 over h. And then hopefully you'll see some kind of good things happen here. So this 9 kills that 9. Once those are done, oh, I still have my denominator. I lost the rest of this denominator. So I still have the square root 2h plus 9, and then I still have that plus 3 out there. Okay, so those cancel, and then I will have this h cancel with that h. Okay, so I'm running out of room. I guess I'll just go here. So I've got the limit as h approaches 0, and basically what I'm left with, right, so I'm left with a 2 over, okay, and then square root of 2h plus 9, and then a plus 3 on the outside. So now when you actually take that limit, okay, as h approaches 0, this piece goes to 0. So I'm going to have 2 over the square root of 9 plus 3. Well, that's just 2 over 3 plus 3, right? So I end up with 2 over 6, which is 1/3. Notice that this time my answer is a numeric output, okay? The answer there is a numeric output, and you get 1/3 there. So what does that mean? That means that if I graphed this, okay, and I looked at x equals 3, so this graph at the point x equals 3, the instantaneous slope, or the instantaneous rate of change right there would be positive 1/3, okay? So I encourage you to pause the video here and attempt this you try it. Okay, so here we have the you try it with another radical, okay? So, and it was evaluated at x equals 6 this time. So when you go ahead and plug it in, you're going to multiply by the conjugate again, and you end up with a numeric output this time of 1/4, okay? So recall that the derivative of a function represents the slope of the tangent line. Guys, we're going to see those words all year long. Slope of the tangent line, you need to be thinking, take a derivative, okay, to the function at a particular point. So when we find the derivative at a certain x value, we're actually finding the slope of the tangent line. So one of the most important things I want you to take from this is that the derivative is the slope. And recall your point slope formula, because you are going to have to use that. So remember, it's called the point slope formula because when you are given a point and a slope, then you can plug it in to write the equation of the line. Okay? We are trying to find the equation of the tangent line of this graph at a particular point. Okay? So what we need to do first is find the derivative at x equals 1, and then we're going to, once we have that derivative, remember this is going to be a numeric output, that's going to be the slope, then we are going to find the x value, which we'll have to get, we know this from part 1 as well, from part A as well, but we'll have to use that, and then we will actually plug that in to the slope formula, okay? So the derivative at 1. So we're going to do f of 1 plus h, okay, so that's going to be 1 plus h squared plus 2, 1 plus h minus 3. So again, you can kind of clean that up, FOIL that out. You're going to get 1 plus 2h plus h squared, right? And then once you distribute that 2, you're going to go 2 plus 2h. You still got that minus 3. And let's clean that up a little bit. I'm running out of room. I'll just go underneath. So that's going to clean up into h squared plus 4h, right? Because this gives you 3 minus 3, those go away, so yeah. Okay, so we've got that, and again, I kind of do that as a size up. Some people do it all in one big step, but I kind of like to break it up. So now I'm saying the derivative at 1, okay? So that means I take the thing I just had, and I recopy it. So I've got h squared plus 4h, okay? And then minus what you get when you plug in, like, so it's minus the original, but I had to plug in 1, okay? So if you want to do that, if you plug in a 1 there, you're going to get 1 squared is 1 plus 2 minus 3. So this gives you 0, okay? So it's minus 0. That doesn't always give you a 0. It just happens to this time. So when I go to clean this up, since that's 0, I'll take out a GCF of h in this numerator and get h plus 4 over h. Okay, oh, I forgot my limit again. So we've got the limit as h approaches 0 and the limit as h approaches 0. So we've got that. Those h's cancel. So you're left with h plus 4, okay? And the limit as h goes to 0, right? If this becomes a 0, so you've got 4. Guys, this is the slope, okay? You need to know that that number there is the slope, okay? Now here, if we wanted to find f of 1, well, we kind of already did that. That's this piece right here, right? So you can kind of revisit if you wanted, but we should already know it from the first part. So you get 1 plus 2 minus 3, so we get a 0. We're just going to put a pin in that. That is going to be, think about it, what did you just do? You plugged x equals 1 into this formula. That's giving you a y. That's giving you an output, okay? So this tells you that there's a point, okay? That implies that there's a point at x equals 1, y equals 0. So now you've got a point and you've got a slope, which makes it a perfect candidate for the point-slope formula. So recall your point-slope formula is y minus y1 equals m, x minus x1, and now it's just plugging in. So you've got y minus 0 equals m, which is 4, x minus 1, right? Because you've got your x1 and your y1 from up there. You just kind of plug those in and clean it up. So my final answer for here would be 4x minus 4. What does that mean? That means that at x equals 1, the tangent line, if I was drawing a line tangent to the graph, it would be this exact curve. So if you had your calculator and you wanted to graph this and graph this line here, this line would touch this parabola at x equals 1. Okay? Okay. Now I did want to quickly mention how to do this on your calculator. So on your calculator, and it only works if you have an x value, like this last one we did. So if you hit the math key, it's over on the left-hand side of your calculator, and then you select choice 8, it'll say end derivative. It'll pop something up that looks like this. You need to tell your calculator this x, because you're taking the derivative with respect to x. You'll need to type this in, and then there's this evaluation bar here that you'll need to type in x equals 1, and when you hit enter, it should give you back that 4 that we got previously. Okay? Your calculator can only find the derivative at a point, not the derivative in general. Okay? So just real quick in closing, the derivative is the slope of the tangent line, and the definition of the derivative, the limit definition of the derivative, you've got the derivative at x is the limit as h goes to 4 of f of x plus h, even though I kept forgetting my limits throughout the video. Don't forget your limits, all over h, okay? And again, you might just want to make a note of that alternate definition of the derivative, because sometimes it shows up. So I just say if we write it a couple times, then it'll at least be familiar for you. So you've got this. Alright, and that is how you find the derivative the long way. And again, those of you in physics, you'll be able to find some shortcuts, and we're going to spend next time in class kind of examining those shortcuts a little bit more. Have a great day. You gonna say bye, Max?
Bye-bye.
Bye-bye.